Okay, Assalamu alaikum wa rahmatullahi wa barakatuh. Today, inshallah, we will start in a new type of machine, which is universal motor. Simply, we discussed before some motors. These are the objectives of today's lecture. We will discuss the steady-state performance of universal motor. We'll discuss the applications of universal motors, and we'll understand the DC and AC excitation of universal motor. We'll discuss the all electronic converters used to control universal motors. This is a chart for the electrical machine or electromechanical machines classification. You know, for electrical machines, we have a classification like AC machine and DC machine. As you can see, we have DC machines like permanent magnet DC motors, like shunt motors, separately excited motors, series motor, and compound motors. We discussed in details the shunt motors and separately excited. Permanent magnet DC motors, we didn't describe it in details. However, it's used a lot in industry. The only difference between permanent magnet DC motors and the field-based DC motor that we replace the field winding by permanent magnets. This is for the DC machines. And you know, compound motor, you already learned it before in 360. It's kind of combining series and shunt windings to make compound motor. And the characteristic of this kind of machine is very close to the separately excited and shunt. And we have AC machines like induction machine and synchronous machine. Induction machine like three-phase, wound rotor, or squirrel cage. And we have also single-phase induction machines like capacitor start, like split phase, and the capacitor start, capacitor run machines. And we are going to describe it in more details next week. So now the classification is mainly according to the type of supply. We have AC machines and DC machines. Also, we have special machines where the supply is not completely AC or DC, or the construction of the machine is special. It's not like in AC machines or DC machines. So what are the types of special machines or special motors? Because we refer all of time to special machines as motors, not generators, because we use it in motoring modes. We have something called stepper motor. We will discuss it in our course. We have brushless DC motor, and we described before brushless DC motor is a kind of synchronous machine, permanent magnet synchronous machine, but it has some special design. We have something called hysteresis motor. We have motor called reluctance motor. It's special design of synchronous machine. And we have something called universal motor. And this is our aim today, inshallah. And we will describe in details what is the universal motor and why we give it this name, why its name is universal. In order to understand the universal motor construction, we will operate a demonstration video here.
دكتور الصوت يقطع.
الصوت مو واضح.
Voice is not clear.
ايوه.
Let me discuss what's said in the video, no problem. Simply, this is the construction of universal motor. As you can see, universal motor, basically, we have stator, core, and rotor core. And as you can see, we have winding. This winding is connected in series. So we have one field winding connected in series with the armature winding. This motor can be supplied by DC or by AC. For that, we call it as universal because it's possible to supply this motor by DC source or AC source. However, there is some different performance between the DC and AC excitation of this motor, and we are going to describe it in detail. So simply, it's series DC motor. However, there is one difference in the construction because we are going to supply it with AC, so we need to make the core in laminations in order to reduce the eddy current loss. So this is one of the shapes. We are going to describe it in one simple shape. As you can see here, this is one simple shape. We have the positive sign is here, and the winding is moving in the bowl of the stator and connected to the brush here, and the upper brush is connected to negative sign. So now we connect it as DC excite or DC excitation. As you can see, the torque is unidirectional for all of time. As you can see here, the torque is in the upper, the force going to the up here, and in the other side, the force is going to the lower side. So this is simply according to the left-hand rule. So as you can see, this is the current direction here, and from the lower side, the lower coil, we have the other direction, sorry. So this is current direction. So it's going to our direction, and the current in the lower coil moving in the opposite direction. So the flux is expected to make N pole in this side, in the left-hand side, and it will make S pole in the right-hand side. Okay, Shabab, is it clear? Do you see the mouse, Shabab, on the screen?
Yes.
You can see the mouse, the cursor?
Yes.
Okay, good. So this pole is N now, and that pole is S. So for all of time, if we supply this machine with DC supply, we will have a flux traveling from the left-hand side to the right-hand side. For that, you will have a torque moving to the to up in that side, at left-hand side, and the torque or force on the right coil of the rotor is moving down here. This is by applying left-hand rule. Okay, Shabab? Right. If we supply this machine by AC supply, what will be the difference? First, for AC supply, the current is varying its direction. So we expect the current moving in the coils will be reversed with time. And also the current which is moving in the rotor coils will be reversed. However, because both of them have been reversed, the torque will be in the same direction. So as you can see, current is reversed and the flux as well will be reversed, and this will keep the force in the same direction. So we will have the same direction of rotation of the machine. For that, if we supply this machine by DC source or AC source, we will have the same motion performance. For that, Shabab, we call this machine as universal machine because we can supply it by DC or by AC. So the principles of universal motor, its single phase series motor, can be used with either a DC source or single phase AC source, as we have described in the operation. And therefore, are called universal motors. So we call these motors as universal because they can be supplied by DC or AC supply. We call it AC supply or DC supply, or DC excitation and AC excitation. Also, there are widely used in fractional horsepower ratings in many domestic applications. We can use it in many domestic applications at homes, like drills, like mixers, like vacuum cleaners. And they are usually light in weight and operate at high speed. As you can see for mixers, for example, the speed of the mixer is very high compared to different kind of motors like normal DC motor, shunt, or series, or separately excited, and induction machine, and so on. So here the speed can reach up to 10,000 RPM, which is impossible, for example, to get it from AC machine. So however, we have used here AC supply, single phase AC supply. The speed here is very high compared to synchronous speed. So this is considered as special machine. We cannot apply the same rules of AC machine on this supply, even if we supply this machine by AC source. Also, universal motors are mostly operated from single phase AC source. Therefore, both the stator and rotor structures are made of laminated steels to reduce the core losses. You know, for AC supply, Shabab, we need to make cores as slices all of time, or laminated steel, because we will have some eddy losses, eddy current loss, and hysteresis loss, and this increases the core loss of the machine. So by making the core as laminations, we can reduce the eddy current loss. So the difference between series DC motor construction and the universal motor construction is the core itself is made from laminated steel, not one single core. Also, high power AC excited universal motors are used in trucks applications. So we can find some applications with fractional horsepower, and we have some applications with high ratings which are used in trucks applications. What will be the performance if we supply this motor by DC excitation? And what are the relations? This is what are going to try now. So the excitation by DC source, if we supply this machine by DC source, we expect to have EMF, which is equal to E equal to K series multiplied by IA multiplied by omega M, the same relation of DC series motor. And also the torque will be the same, K series multiplied by IA squared. You remember the general form of relations in case of shunt or separately excited. The EMF for separately excited motor was K multiplied by flux, or IF, multiplied by omega, which is speed. And because this motor is series, so the field current is the same like armature current. So we can multiply K phi together, and we have instead K series multiplied by armature current. So this is especially for series DC motor. So we have the same relations of DC series motor. Simply, in order to draw the torque speed characteristic of this machine, we can get the speed relation. You know, we can get the speed from this relation. Omega will equal to E divided by K series by IA. So simply, this is omega. And we can substitute by E equal to V terminal minus IA multiplied by all of the resistances which are connected in series. So this is a circuit of DC series motor. We have series winding resistance. We have rheostat or variable resistance to control the speed of the machine. And we have armature resistance. So we can add all of these resistance together in order to calculate the total voltage drop here. So I multiplied by the total resistance will equal to the total volt drop here. So simply we can say V terminal minus IA multiplied by RA plus R series plus R rheostat equal to the EMF of the machine. So simply we can say V terminal divided by KS or K series IA, this is one side, and here IA divided here by IA, so can omit it from the relation. So the second part will be RA plus R series plus R rheostat divided by K series. Simply, we can substitute IA equal to square root of T divided by K series. So we can substitute this here instead of IA, and we can plot a curve between omega and torque at different values. It could be found that we have the same characteristic here like in series. This is series DC motor. So these are the characteristics of series DC motor. And as you can see, by changing the value of rheostat, we can go in this direction with the characteristics. So we can make speed control by means of changing our rheostats. So this is the performance characteristic of DC series motor. As we described earlier, DC series motor has the advantage of having high starting torque at low speeds. And when the speed increases, the torque gradually decreases. So it's very useful to work with high starting load applications. For AC excitation, we can replace the supply by AC source. So we expect to have AC current and AC flux. The eddy current effects are neglected. If we neglect the eddy current effect because of the laminated sheets, the current IA and the flux phi D are in phase. You know, for any kind of machines, we have two components of fluxes. Flux in the direct quadrature and direct axis, and flux in the quadrature axis. Here we will have the direct X in phase with the armature current. So we expect to have EMF in phase of current for this machine. So for all of time, IA and the EA will be in phase. If we assume an electric current IA equal to IA maximum cosine omega t, and phi D, which is equal to phi D maximum cosine omega t as well. So we can calculate the instantaneous EMF as EMF equal to machine constant multiplied by flux multiplied by speed. So it's Ka multiplied by phi dm multiplied by omega m cosine omega t. Take care all of time. The symbol phi here is instantaneous because it's small letter. And here phi dm means maximum value or peak value of the cosine wave. So if we would like to calculate the RMS value for EMF, simply it will be this value divided by square root of 2 because it's sinusoidal waveform. So it will be Ka multiplied by phi d maximum divided by square root of 2 multiplied by speed, which is equal to Ka multiplied by phi d, which represent the RMS value of direct flux multiplied by the machine speed. And simply we can replace Ka phi d by K series Ia, which is the normal relation for series motor, where K series is the series constant for machine, and Ia is the RMS value of the armature current. So simply, this is the relation now of the EMF. As you can see, it's the same relation of the EMF in case of DC machine. So this means if we have, or if we supplied a machine by AC and DC, we will have the same EMF if we consider that we have a similar value of current, IA, equal to the same average DC current. Also, in order to calculate the average torque, we need to calculate the torque from the equation, instantaneous equation. So torque as a function of T equal to Ka multiplied by flux as a function of T multiplied by current, also as a function of T. So these two functions are equal to phi maximum and I maximum. Here is cosine omega t, and here is also cosine omega t. So the relation will be Ka phi d maximum, Ia maximum, cosine square omega t. Or we can represent it in RMS values as, we can replace cosine square omega t by 1/2 multiplied by 1 plus cosine to omega t. So this is the relation which represents the instantaneous torque. However, for torque, we need to calculate all of time, we need to calculate the average torque. So average torque is equal to, we need to make integration for this relation for one complete period. So you can make this relation easily and find the final form, which will be Ka multiplied by phi d multiplied by Ia, where phi d and Ia are the RMS values of flux and the current distribution. So we can replace this relation also by K series Ia squared. So this is the relation of torque. Right. What is the difference now between DC? We have some relations for the electromechanical or electromagnetic developed power. How we can calculate it for DC or AC? It's simply developed power equal to EA multiplied by IA. So it will be the same. So we can say torque developed equal to B gap divided by omega m, which is EAIA divided by omega m. And this is the mathematical model or mathematical representation for the universal motor in AC excitation. So V terminal equal to IA multiplied by R total plus JX total plus EA, where R total is the sum of total resistances like field circuit and armature circuit, and the same also X total represents the reactance of the overall windings XF plus XA. So simply, this is the phasor diagram. As we described from the beginning, we have current and EMF in the same direction. So if this is the direction of IA, and we need to represent this mathematical model, so IARA will be in phase with IA, so this is IARA, plus EA, plus JIAXT, which is perpendicular to the current direction, and the sum of this relation will be the terminal voltage. So this is here VT. So this vector represents the terminal voltage. Right. What is the angle between voltage and the current for any machine? This angle. Yes, the power factor angle, exactly. So if we would like to calculate the power factor here, we can say this length divided by this length. Is it right? Mm-hmm. So the power factor here equal to IAR total plus EA, all divided by V terminal. So this will represent the value of the machine power factor. In DC excitation, we don't have power factor, because in DC excitation, all of vectors or all of values are in phase, and there is no angle between voltage and the current. All of values are considered as scalar values. So now we calculated the excitation in DC and AC. what is the difference between DC excitation and AC excitation? In terms of the machine operation, it will rotate in the same direction. There is no problem. However, there is some differences in the performance if we compare the DC excitation with AC excitation. Simply, if we compare the EMF as we described before, EMF in DC equal to K phi multiplied by omega. And here is in AC also, it's K phi multiplied by omega. If we assume armature current for DC excitation and the root mean square value of armature current in AC excitation are the same, so if we expect similar currents, in this case, we will have Ka multiplied by phi here equal to Ka multiplied by phi for AC. And this means this term can be represented by only omega m in DC, and this part represented by omega m in AC. So if we compare the machine at the same current, we can say EDC divided by AAC equal omega DC divided by omega AC. And this relation is important to solve problems. Also, if we compare the EMF relation where or at different excitation currents, so for DC excitation, Shabab, we have V minus IA multiplied by the total resistance. This is represent the EA. However, for AC excitation, if we consider different currents and different excitation, so we can say for EAC equal to V cosine theta minus IA multiplied by R total. This relation comes from the phasor diagram. If we return back to the phasor diagram here, this is V terminal, and this vector can be represented as V terminal cosine theta. So we can say V terminal cosine theta minus IAR total equal to EA. So this is now the relation for AC excitation. If we divide it by V in the numerator and denominator, as you can see, this will be 1 minus IA divided V multiplied by the total resistance. And this one here will be cosine theta minus IA divided by V, as you can see, multiplied by the same resistance. Comparing numerator and denominator, this part can be considered very small because it represents the voltage drop on the resistance in per unit. So if you have current of, for example, 1 ampere and total resistance of 10 ohms, and you have voltage of 500 volt, you will have value here of 10 divided by 500, which is very small value. And the same will be here. So if we neglect this part from the equation, we can find that EDC divided by EAC equal to 1 divided by cosine theta. 1 divided by cosine theta will be greater than 1 for all of time. This means in case of having different currents from DC and AC excitation, for all of time, the DC excitation will be higher than the AC one. So this is very important and expected, because you know, when you supply, if you have certain impedance, and you supply this impedance by DC voltage and connect another the same impedance to another AC supply, is it expected to have higher current in AC or DC? This is a question for you.
DC.
DC will have higher current. Why?
Because will be less impedance.
because there will no reactance in the circuit. Is it right?
Yes.
So
Yes.
reactance in DC steady state will be 0. So it's expected to have lower total impedance in case of DC. So you will have higher excitation in DC compared to AC source. So this is expected in this kind of machine. Right. So
Victor, can you repeat that again, please?
again, this derivation you mean, or the example?
No, just the last point, Victor.
Last example. We said if we have certain impedance, and like that, I will write it down here. So you have impedance like that. And you supply this impedance by DC source. And you have here R and XL. So in case of DC, what will be the value of current? IDC. It's equal to VDC divided by R. But what if you have here VAC with the same value of VDC? So expected to have IAC equal to VAC divided by R plus J. So here you will have lower current for AC supply. So this means DC excitation will make higher induced voltage or higher current. Is it right, Shabab? And this is what expected for such motor if we supply it from DC and AC. Okay, is it clear now?
Yes, Victor.
Okay. So continue for the characteristic. If we have such characteristic now, and we would like to plot the characteristic of the machine, as you can see, you will have difference between the two characteristics according to the DC and AC excitation. So if you assume the same speed at the same speed here, so assume we have constant speed, you will find the torque at AC is lower than torque at DC, which means the power of DC will be higher than the power of AC. And this is also expected because we have a higher excitation in case of DC supply. Is it clear, Shabab? So the power of DC can be higher than the power of AC at the same speed. And also at the same torque, if you would like to compare at the same torque, it will be the same. I mean, we can erase this part and compare if we used the same value of torque. So assume we have constant load torque here. This means if you supply it by AC, you will have lower speed compared to the same machine if you supply it by DC. So you will have higher power in case of DC. Is it clear? Okay. This is a simple example. 120 volt, 60 hertz, 14 horsepower universal motor runs at 2000 RPM and takes 0.6 ampere when connected to 120 volt DC source. So this machine, we started here with the nameplate data. As you can see, this is the nameplate data, 120 volt, 60 hertz. However, from here, it's stated that universal motor runs at 2000 and takes 0.6 amps when connected to 120 volts. So this condition is for the DC excitation. So if the supply is 120 DC, the machine will run at 2000 RPM and the machine will draw 0.6 ampere. So what is the requirements here? To determine the speed, torque, and power factor of the motor when it's connected to 120 volt 60 hertz supply and is loaded to take 0.6 RMS current. So this means the machine will draw the same value of current. Same value of current, so we can compare the EMF of the two motors or the two cases. So the resistance and inductance are given as 20 ohm and 0.25 henries, respectively. In order to get the speed for the AC excitation, we need to compare the EMF for both DC excitation and AC excitation. Let's start with AC excitation. We have total reactance equal to 2 by F multiplied by L. So 2 by F, 2 by 60 multiplied by 0.25 henries. You will find the reactance of 94.25 ohms. And simply you can calculate E from the phasor diagram using this relation, which is V terminal minus V terminal square minus IA square X T square, which is using Pythagoras, which is this length, and we can subtract the value of IAR total to obtain the value of EA. So simply you can substitute here 120 square minus 0.6 multiplied by the reactant total square minus current multiplied by the resistance. So this is the value. Sorry, it's should be 93 point, not 93 Z. So let me correct it now. So this is decimal points. So this will be the value of EMF here. In case of DC excitation, if the supply is 120, the same, so we expect to have EMF equal to 120 minus 0.6, which is the armature current, multiplied by the total resistance. So we have 108 volt DC excitation. So simply, when we compare the two excitations together, E in case of DC and E in case of AC equal to RPM in DC divided by RPM in AC. So we can say RPM in AC equal to RPM in DC multiplied by E in DC, sorry, in AC divided by E in DC. So simply, this will be the value of speed in the AC excitation. For all of time, you will have lower value of speed in AC excitation compared to that of DC excitation. So this result is logical. Right. Also, it's required here to calculate the torque and power factor. So simply, if we started with the power factor equal to cosine theta, which is EA plus IARA divided by V. So simply we calculated the value of EA and the value of IARA, which is 0.6 multiplied by the 20 ohm resistance, which is 12, divided by the supply voltage. So this is the value of power factor. I have a question for you. Why here we use E without angle and V without angle? Do we need to use angles here?
No, magnitude, Victor.
Just magnitudes, because we compare this triangle, is it right? We
Yes.
to this triangle, so we don't need to use vector. We just use scalar values. Okay. In order to calculate the mechanical developed power and torque, in order to calculate torque, we will get it from the mechanical developed power. You know torque, we can calculate torque as K phi multiplied by I series square. However, we don't have the value of K series here, so we can calculate it using the developed power of the machine. So simply, the mechanical power equal to E multiplied by I. So this is the calculated E, and this is the value of given current. So this is the value in power. This is the developed power of this machine. So for now, the torque will be d mechanical divided by omega m. So this is the speed. In RPM, we have to multiply by 2 pi divided 60 in order to get the value of torque. So this is the value of our torque here. I have a question for you. Now, the power here is 56.3. And in the beginning of the machine, it stated that the machine is 14 horsepower. Is it small power according to the 14 or not?
Yes, Doctor.
Small or not?
Yes,
It's very
small.
small. Is it right? Because
Yes.
14 horsepower, if you multiply it by 0.745, you'll have the value in kilowatts, which it should be very high compared to that small power. Why this happened?
Losses, Doctor.
Sorry?
Losses.
No, it's not losses. Because if you calculated the losses here, and if we consider the cover loss here, it will be 0.6 square multiplied by 20, which is small value as well. Is it right?
Yes.
But take care, this is not the rated operation. It's not the rated condition. This loading condition here is not rated value, because if you have 14 horsepower, this means how much?
10K. 10 kilowatts, Doctor.
Around 10 kilowatts.
Yes, around 10 kilowatts.
Okay, so 14 multiplied by 0.745, it's 10.43 kilowatts. If you divide this value by the value of 120, you will have rated current around 86 amps. And here the current is 0.6 amps. It's almost no load. For that, you have very small torque value. If you find the torque here, it's 0.3 Newton meter. However, if you calculate the rated torque of the machine, it should be very high. Okay, شباب? Okay. Any question? So this is simply the our discussions in universal motor, and most of references in universal motor describe very short parts, and for that also we will discuss only short part about the universal motor, and we will have one experiment regarding this motor in order to compare between DC excitation and AC excitation. We'll describe it later, inshallah. Another important part regarding this machine is the control circuits. How we can control this kind of motors. And for instance, you have in homes, you have mixers, you have vacuum cleaners. And for high power machines, we said we can use this machine in trucks application. So it needs a controller. And for small appliances, we can consider any kind of conventional control technique by adding resistance, for instance. However, for high power machines, we have to use electrical drives. So what is the electrical drive that can be used in either cases, either in DC excitation or AC excitation? For DC excitation, we have two options. If we have the supply as AC, so we can use controlled rectifiers. But this is not available a lot in trucks, because trucks may take DC supplies, not AC supply. This is for electric vehicles and also for powertrains. However, if there is a powertrain with AC supply, you can use controlled rectifier. The mostly used one is the DC chopper. We described before the DC chopper. DC chopper will make lower losses for the machine because you can control the rebels and you can have high performance compared to rectifiers. So it's preferred to use class A DC chopper if you are going to operate the machine in single mode, which is motoring mode. However, if you would like to operate the machine in 4 quadrant modes, you need to use class E DC chopper, which is the 4 quadrant. In case of AC excitation, we can use AC voltage controller يا شباب. Simply AC voltage controller is nothing but back-to-back thyristors, or a device called TRIAC. TRIAC is also can be considered as back-to-back thyristors. So we can use the AC voltage controller to control the performance of this machine. So this is what we need to describe about the universal motor, a summary for what we have described. We discussed the construction of the universal motor and also the operation. We discussed the characteristic, torque speed characteristic of universal motor. We described the DC and the AC excitation and what's the difference between both of them and what's the difference in performance. And also we discussed the drive systems that used for universal motor. Thank you, Shabab.